All right, today what we're going to do is we're going to take a look at an application of derivatives, which is basically the same thing that we've been doing pretty much in the entire chapter 4, which is we would like to be able to determine where the extrema of a function is. This idea of this optimization is when you're looking for an extrema, you're looking for your maximum or your minimum. And in most real-world application problems, it's things like where we are actually looking for the biggest and the smallest, cheapest, strongest, ugliest. That's kind of a funny there, but your idea is you're always trying to find the lowest cost or the largest profit or the minimum amount of work. So there are a lot of problems where you are actually looking for your extrema, and we call that concept, this idea that in a real world problem that we're looking for a max or a min, an optimization problem. Now, usually when you're trying to find this optimization problem, you need something that limits the, the item, what you're trying to optimize. And usually that comes in the word problem, in that you always have to have that limiting factor. And basically it's a constraint that is going to keep the item from growing without bound. And so that way you have two things that you're going to be looking for in these problems. You're going to be looking for a equation or a function for whatever item you're trying to optimize. If you're going to optimize the area, maximize the area, you need an area formula. If you are going to maximize your profit, you need a formula for your profit. The formula for the item you're trying to optimize typically has more than one input variable, because there's usually some relationship going on between two or more variables. And usually that's where the constraint is going to come in, that you're going to use the limiting factor is the constraint that relates the two variables together and limits the growth of one variable or another. And so that's what we're going to be looking for. Kind of one thing to remember in this unit, we're looking for absolute extrema, not just relative extrema. So things like the first and the second derivative test are going to have to be modified so that we're getting absolute, not just the relative extrema. And we'll talk about that below. There's going to be three methods that we're going to work with. The first method should be obvious if I'm going for an absolute or global extrema, which is extreme value theorem. But we do have to remember that extreme value theorem requires the function be continuous on the closed interval, differentiable on the open interval, and you must have a closed interval that you are considering in order to use the extreme value theorem. And then the other two methods, we're going to modify our first derivative test for extrema, and we're going to modify our second derivative test for extrema to get a third method. These are challenging problems, I'm not going to lie to you, because we're doing the dreaded word problem. You have to be able to read through the problem, and you have to be able to identify the pieces of information that you're going to be looking for. When I say read the problem carefully, what are we looking for? You're looking for things that you're going to optimize, your max or your min. Drawing a picture is always a good thing if you're trying to kind of see what's going on, trying to find relationships, what your variables are going to be. So a picture is usually a good thing to start with. So you kind of read the problem, draw any pictures that kind of show what's going on in the situation. You're going to label any variables. If you have any constants, you're going to label those. Things are going to be the same throughout the problem. And this is just kind of a little bit of a tip when you are labeling something. Like, for example, if I'm labeling this part right here, usually what you're going to try to do is, like if I had no idea what the length is, but maybe I know this part of it is 10. Instead of calling this part the whole x, what I would rather do instead is call the little part x, and then that makes the big part 10 plus x. And that usually is just kind of a standard that kind of helps you come up with simpler formulas when you're doing this. And that's always good if you have to take a derivative. So if you can avoid a fraction, avoid subtracting, there are different things and reasons for that, but typically that's what you want to try to do. What I'm contrasting this with is versus if you had the same scenario and you called that 10, you called this x, and then you call this 10 minus x. That it's okay to do that, but it does typically lead to more complications. So you do try to go with this version. Label the small parts as your single variables. When you read through the problem, the very first thing you got to figure out is what you're trying to optimize. And I would also make sure you identify whether you are maximizing. Are you looking for a maximum? Or are you looking for a minimum? And so that's going to give you this idea of what you're going to be doing in the problem. The other thing is once you determine what you're maximizing or minimizing, you need to find a formula. Okay, your primary equation is basically just a formula about the object or item that you are maximizing or minimizing. For example, if I want to maximize volume, I go find the volume formula for whatever this object is. If I want to maximize area, I use an area formula. So you basically have to come up with a, hey, what am I optimizing? What is a formula that I know about that? Then you're going to read through the rest of the problem, and you're going to try to find your limiting factor or constraint. Usually that's things like if you are optimizing the volume of a cone, then you have the volume formula for the cone has your radius of the base of the cone and then the height. And so you're looking for some piece of information in there that's going to relate your radius to your height and give some kind of a restriction on it. Like your height can only be twice your radius or something like that. And that's going to help us find and simplify our primary equation into one input variable instead of two. So once you get number 4 and 5 kind of go together, you're going to immediately take that secondary equation, the one that relates your input variables, solve it for a convenient one. It usually doesn't matter, but we do want to try to plan ahead and say which one do I solve for gives me the easiest derivative. And go ahead and do that, and then we substitute. So the whole point of this part of the problem is for you to substitute into your primary equation so that you get it down to one input variable instead of two or more. Okay? Usually once you have that primary equation with one input variable, you do want to simplify. This is more to make it easier for us to take derivatives. And that's really kind of our goal. So it's kind of like, hey, let's simplify it so it's set up to take a derivative. This is going to be a very important key point to this, and this kind of helps us figure out sometimes what method we're going to use, whether it's going to be the EBT or the modified first and second derivative. What you basically want to do is look for a relevant or feasible domain. In the real world or in the context of this problem, your input variable that you have left, what would be the realistic domain for that? Sometimes you're lucky and it is a closed interval, and then you're going to be allowed to use EBT. Sometimes, in a lot of the problems, it might be 0 to infinity because you have an area or a length, and a length cannot be negative, and so there are things like that. But you also kind of have to look at your constraint, because your constraint sometimes will give you, hey, I know that the radius has to be positive, and I also have some restrictions based on the constraint, so I get a max value, kind of a bounded feasible domain, is what we're going to be looking at. So you always then go to differentiate, because to identify critical values, you are basically looking for your first derivative. Now we pretty much, even though we're still going to say, hey, your first derivative doesn't exist, it's going to give you critical values, most of these problems are really going to be critical values from where your derivative of whatever function you're doing is equal to 0. I'm not going to say 100% of the time, but most of the time that's really what you're looking at, because we're looking for the maxes and the mins. We're going to determine the absolute extrema and justify with calculus. That's going to be our 3 methods: EBT, modified first, modified second. And then this is kind of important, I keep harping on this, is that you need to make sure you answer the question that they ask you and use appropriate units, okay, in order to get your question. So this part right here is kind of, after you get your equation, this is all pre-work. 1 through 5 is basically you trying to figure out how I'm going to set up this problem. What do I have to do? What formula am I going to use in order to differentiate? Then when you get down here to 6, 7, and 8, this is the actual calculus part of, hey, I'm running the actual test to find the max or the min or find the extrema. And then, of course, you have to finish it up and answer the question that they have asked you. Right? So let's go to the next page. Let's talk about our 3 methods. Get those kind of out of the way before we start doing some examples. The first method, we've already spent a lot of time talking about this, but we're basically going to be using the EBT. You have to have relevant endpoints. When you are figuring out your relevant domain, the domain that makes sense in this problem, it has to be a closed domain. You have to have from a value A with a bracket up to a value B with a bracket. It has to actually be that closed interval domain when we are looking at the problem. And kind of a few examples of where this occurs, but it doesn't always occur. You also have to make sure that you should identify the two criteria for EVT, which is your function, whatever it is, must be continuous on your closed interval and differentiable on the open interval. So we do want to make sure that we check that as well to make sure that this method is the appropriate method to use. Okay. Of course, this doesn't work most of the time for these problems because sometimes you have an unbounded endpoint. You might have something like a to infinity or even an open a to infinity that we have to worry about. We also have a lot of times where you might have the domain is over negative infinity to infinity. That's not impossible, but we do want to make sure that we are looking at that. Now, of course, when we're doing the modified first and modified second, you still have to have a continuous. Pretty much you do have to have a continuous function for either of these three methods, which of course they won't be asking you this problem unless it is continuous on the AP anyway. So if I don't have two endpoints in my domain, I'm going to use either first or second derivative test, but modify. When we modify the first derivative test, what you're going to do is you start out the same way. You're going to differentiate, find your critical values. And then what you want to make sure is this is the always is the part that's going to turn a relative into a global, because relative is only for some interval is this true, where we're going to be saying for on the domain, okay, when I say always, we're basically saying on the entire relevant domain that you have to show that that relative max, like before that relative max, your function is always increasing, or your first derivative is positive, and after that it always decreases, your first derivative is negative. And if you can show that, then you would be able to say that you do have a global max. And then of course you would switch it for your global min. It should be decreasing and then increasing, or negative first derivative, positive first derivative. All right, so that's how we're going to modify. We just have this extra little, we have to talk about what happens on the entire relevant domain in order to get that. This third method, your second derivative test, just like the second derivative test for extrema, is you find your critical values from the first derivative. Remember, you're still using the first derivative to get your critical values for the extrema. Then we find the second derivative and we determine if the function is, and again, here's that key word, always concave down or always concave up in your relevant domain. And basically, if you know that you're concave down, then you must have a max, and it will be global because it's concave down the entire time, or always concave up. How do I choose which of these to use? Really, it just depends on what I think is the easiest. If it's really easy to get a second derivative, especially for some of these polynomials, a lot of times I will do that. But if I already have a sign chart for a first derivative, then I don't necessarily need to do that. Sometimes what you'll see is you could do the sign chart, but picking numbers and plugging it in, sometimes it's a little difficult to determine the positive, negative. But if you found the second derivative, it's very easy to determine because it's either always negative or always positive, that sometimes that's a little easier. And we'll kind of show several examples working it both ways. Okay? And again, the idea is when you modify these, you've got to make sure that it's working for all values in the relevant domain in order to get the global argument justified. All right, so let's go ahead and let's jump right into the first example and kind of see how these word problems work. All right, so our first example, this is a classic problem that you basically see in pretty much any algebra class. Too, you kind of have this idea where like trying to find numbers for which something is happening. So let's read through the problem. We want to find two positive numbers. We want their sum to be 60, and they want the product of one times the square of the other is a maximum. Okay, so step one is figure out what you want to maximize. And right here is where the word maximum is, and I'm maximizing what? The product. So I kind of start coming down here and I say, what am I going to do? You're going to want to make sure that you inform the reader in the FRQ what is it you're doing, maximizing or minimizing. And we're going to maximize product, so you pick something to call. I'm going to call my function P. And then you go, well, what's the formula for this product? Well, they kind of gave it to you here. If you just read through the problem, you're getting, it's take one number times the square of the other number. So name one number X, name the other number Y, and so one number times the square of the other number. So that gives us our kind of problem. Now there's not a picture to draw in this case. If I have variables, I do want to identify them if there's no picture that shows what they are. So I might come over here and go, P is going to be my product. I'm going to say X is going to be the first number, and Y is going to be the second number. So give the FRQ reader an idea of what your variables are, unless it's clear from the picture that you've drawn, but we didn't have a picture here. So that's kind of step one. All right, step two is to come in, and now we need to figure out our constraints. So I go, all right, what else do I know? And remember, the constraint or the limiting factor is going to relate X and Y together, the two numbers. So I read through the problem and I say, is there anything that I know what relates the two input variables, X and Y, my two numbers? And we'll see right here that we've got the two positive numbers and their sum is 60. So what we want to do is we want to say, okay, that's going to give me my constraint that I'm going to be looking for. So we go ahead and we say, all right, what does that mean? The sum is 60. So X plus Y equals 60. Now once we have that, the whole point of this is to now go ahead and use this equation, solve for one of the variables, and then plug it into this one so that our product now only has one variable in it, so that we can differentiate fairly quickly. Now, you have two choices. You can either solve for Y and plug it in, but then notice that's going to involve squaring 60 minus X, which would be more complicated than if I just solve for X. And when I get X is 60 minus Y, I don't have to square it. So you do try to think about, as you are plugging this in into your product formula that we have above, that you want to choose the easiest version. And so in this case, I'm going to change it to 60 minus Y times Y squared. Now, a lot of times right here, I go ahead and simplify this, get myself ready to take the derivative in the steps that are going to be coming. This ends up being 60Y squared minus Y cubed. Now, before you're ready to move on right now, what we want to do is we want to go ahead and determine the relevant domain, because we need to know that to know what method we're going to use. All right, so everything that I've done so far right now, I have the setup ready. So I have determined what I'm going to maximize. I have determined my constraint. I have solved the constraint down here for one variable, one input variable, and so I'm ready to actually now do the work, which is the calculus portion of this. So everything that's here was nothing more than your setup. Okay? Now we're going to do the calculus, and we're going to determine our relevant domain, and then decide what method we're going to use. So our relevant domain, when we take a look at this, is we say, all right, Y is this number, and it's positive, so that's the first thing we should notice. So it has to be 0, and the sum of these two positive numbers is 60. Now let's think about it. If I add two positive numbers together, what is the biggest value that it could be? I mean, could it be 75? The answer is no, because the other number is also positive, so the only way that two positive numbers add to 60 is they have to pretty much be between 0 and 60. So now, in looking at this, you go, do I have a closed domain? The answer is no, so you can't use EBT. So right now, we pretty much know we're either using the first derivative modified or second derivative modified. All right, so let's go ahead and just get started on the problem. We know we always start by taking the derivative, so we're ready to go. All right, so our first derivative is going to be, we'll go ahead and label it down here, P prime equals 120y minus 3y squared. So that's fairly easy, straightforward to do. Let's go ahead and factor it. I can pull out a common factor of 3y. I'm left with 40 minus y. And as soon as I get to here, I can immediately go, that derivative is equal to 0 when y equals 0 or 40. Now, as we are working through the problem, we recognize that that's not in our relevant domain, don't have to worry about it. So we're now just looking at our one critical value of 40. Now, there's two things we do. We can do the first derivative test, and we can determine that on the interval 0 to 60, that it's always, because I'm looking for a maximum, that it's always positive before and negative after for the derivative. Or I can go ahead and find the second derivative and show that it's either always positive or always negative. I'm going to go with the first derivative. So we're going to use the modified first derivative test. If you want to do your little sign chart, that's fine. We can put our 0 and our 40, and then I'm going to put 60 here because I only care about I don't care what happens over here. I don't care what happens over here. I only care what's happening in the relevant domain. I say, what do we know about the derivative? It's a 0 at 40, and we know that this is a quadratic with a negative lead coefficient, and so it basically, because those are your two zeros, it was 0 over here, I'll go ahead and just fill it in just so I have that it's going to have a negative and then a positive, and then over on this side it would be negative. So we can pretty much just look at that and fill it in. And we see that on our entire relevant domain, it always is positive before, and it's always negative after. The word always is the key. All right, so we're going to make our calculus conclusion, and our calculus conclusion is y equal to 40 maximizes P because, okay, and here comes our calculus reason, our P prime of T is greater than 0 for all, oops, I don't know why I said T there, what was I doing? P prime of Y is greater than 0 for all Y in our interval, 0 to 60. Well, actually, where do I want to stop that? I don't want to go 0 to 60, it's till 40. That's my always positive before, and your derivative is always negative for all Y from 40 to 60, okay? So you just want to make sure you're getting in that for all. Now, before I'm actually done, let's see if that answers the question they asked me. It said find two positive numbers. So I haven't actually answered the question. This part right here is the calculus that then found the maximum. Now that I know that, then what I want to do, I hope I spell correctly, maximizes, is answer the question. And I've not left myself enough room, so I'm just going to come up here to the top. And the answer is the two positive numbers are 40 and 20. And we've answered the question. Okay? So there's your setup, your primary, your secondary, solve, substitute, and simplify. Then you have the calculus, determine what relevant domain, choose a method. We chose a modified first derivative test this time. And then determine the maximum, give your calculus reason, and then answer the question. And those are the steps to an optimization problem. Okay, moving on to example 2, we're going to take a look at another classic problem. I like to take these little pipe cleaners and we're going to bend them and form different shapes with them. And for this problem, we're going to be forming a rectangle. And so again, you're going to start with your setup. And that setup, you're going to find what you're trying to maximize or minimize, write your formula, find your constraint, solve your constraint and substitute, and get yourself ready to take a derivative. All right, so in the problem, we read through it, and we're like, what am I trying to maximize? You know, now if you're in a hurry, you can actually say, hey, I'm going to go down here to the end. I see the word maximum, and I go, what am I maximizing? I am maximizing area. You might want to say area of what? A rectangle. That's the shape that I am going to be forming. I might go ahead and draw a picture with this one. I have my little pipe cleaner, whatever that is with the length, and I'm going to take that pipe cleaner and I'm going to bend it so that it forms a rectangle, okay? And so that as we're looking at this, then we go, well, how do we find area? We are maximizing area, and we know the standard formula for area is length times width. So we'll go ahead and we'll label that in the problem. So I don't have to identify variables because I have a picture, you know what they are. Then I come in, I look for my constraint. The constraint relates the length to the width. And so you look through the problem and you're like, okay, well, what do I know about this length and this width? And you're like, oh, wait a minute. Is there anything in there? What do I know? Well, the first thing is you have to kind of go, wait a minute, they gave you that it was an 8-inch long pipe cleaner. So this is 8 inches long, of which I'm bending it up into this shape. And the outside length around is the perimeter. What do we know? Like if I were to unbend this and put it back up here, how many of these sides are there going to be? There are going to be 4. You're going to have 2 of the widths and 2 of the lengths when you bend it around and make your sides. So we know that 2L plus 2W has to equal the 8 total inches that we're looking at. Now in this problem, does it really matter which one you solve for? No, you can pretty much just choose what you want. I'm going to go ahead and choose the width and solve for that, although you could have done length, it doesn't really matter in this case. So our 2W would be 8 minus 2L, and W would be 4 minus L. So this is going to allow us to substitute and create our primary equation with one variable. We put it in, 4 minus L times L. Simplify it, 4L minus L squared. So we get to that point, now we're ready to take our derivative. So we're now on to the calculus portion here. We're going to find our relevant domain. And clearly, if you are looking at your length, in order to actually fold and have something, your length has to be bigger than 0. So we'll go with 0. And is there a maximum to it? Well, yeah, you can't have a, technically, if we're being really technical here, because there's 2 L's, that you can have up to 4, but you can't include 4, because you got to have 4 for one side, 4 for the other. So you got to be a little bit less than 4 to have a little width to it. And that would probably be, again, our relevant domain. Would also say, notice it's open, so can't use EBT. So we want to do a modified first derivative or a modified second derivative. I'm actually going to do the modified second derivative this time just to show you kind of what the difference is. But either way, you start the same way. We find our derivative. Our first derivative is going to be 4 minus 2L, and since I'm going to use planning ahead, I'm going to use the second derivative, modified second derivative test. I'm going to find the second derivative right now, which would be minus 2. Now, and this is a reason why this is the modified second derivative, because whenever I see this, I know that this is always negative, which means it's going to be very easy for me to use the modified second derivative test because I can get that conclusion of it's always concave down. And so that's going to be our method that we're going to use. All right, so come back over here. What are my critical values? I know that when A prime equals 0, when L equals 2, and that's the only one, so that's the only one I have to worry about. We already know that the second derivative is always negative, so now we're ready to make our calculus conclusion. So our A double prime of L, which was my input variable, is less than 0 for all L in the relevant domain, 0 to 4. It's actually everywhere, but I can say in the relevant domain. And so what does that mean? That implies that A of L is concave down for all. So your L equal to 2 maximizes the area. And then we're done. So that one's actually a fairly quick test. Then I have to go back. Now I have to make sure I answer the question. You get so excited that you're done with the calculus part, but you do want to make sure that you actually answer the question that they ask you. So we come back up here and say, what did they ask me for? The dimensions of the rectangle. And so I go, all right, well, I know that the length is 2. So the dimensions are length of 2, and when L is 2, then so is the width, and width
of 2 as well. Which a lot of common sense would have probably told you that a square is going to be the biggest area that you can create, but you don't get to use common sense on the AP. You actually have to show the calculus that justifies it. All right, let's take a look at the next example. This one is a classic where you're going to take some fencing and you're going to make some type of a field, and notice that we're going to be trying to find the largest grazing area here. So right there I have the what am I trying to optimize? I'm trying to find the largest grazing area of what? I read back through the problem and see that it's going to be a rectangular fence. So I'm again going to start by drawing a picture just to make sure. One thing that you might want to notice is that we're bordering on a straight river, okay? So there is no fence along the river. That's going to be important when we set this up. So even though I'm going to put a river here, that's not part of the fencing. The fencing is really just these 3 sides. So you want to make sure you pay attention to those types of things, whether you have fence all the way around or only in portion of it. And we're looking for dimensions of the field, so we can do length and width again. Our area formula, just as before, area equals length times width, and we are maximizing. We take a look for our constraints. So is there anything that we know about the fencing that we have? We have 500 inches of fencing. So that's our constraint that we're going to be looking at. So our L, now the fencing is going all the way around here. So I have L plus 2 of the width has to equal that 500. That's going to be the constraint that we're going to be looking at. Okay? And solve your constraint. Does it matter which one we solve for? Not really. Just so I don't have to divide by 2, I'm going to solve for L. L is 500 minus 2W. I substitute that in, so my area formula becomes 500 minus 2W times W. I go ahead and simplify for the derivative. 500W minus 2W squared. Okay, we go on to take the calculus portion of it now that we're set up. So let's start the calculus. We look at our relevant domain. Okay, in our relevant domain, let's say that we know that our width has to be at least 0 because we're trying to form a field. And this width, now because I have 2 of them, and I'm going up to 500 feet of fencing, that I have to be less than 250 because I need to have 2 of the widths, and then you gotta have some length, so it has to be less than that. So again, still can't use EBT. It's going to either be modified first or modified second. Go ahead and start finding your derivative. So that way we'll know which one we're going to do. Our derivative would be 500 minus 4W. Since this is linear, I'm going to go right to my second derivative, and the second derivative would be negative 4, which is less than 0 for all W in the 0 to 250. So I'm going to set myself up right there for the modified second derivative test. And then we go ahead, our critical values. When A prime is equal to 0 would end up being, let's see, we have 4W equals 500, or W equals 125. We can go right to our conclusion. We know that W equals to 125, I don't know if I was doing this before, but I better start making sure I put in units, inches, maximizes area because your second derivative was less than 0 for all W in the relevant domain, 0 to 250. And then I'm going to answer the question. The question is asking for the dimensions of the field. So again, the dimensions of the field would be 125 inches by, and if I have 125, that would be 250. And then we're done with that problem. So you'll start to see that a lot of these types of problems are fairly formulaic, and you can get through them fairly quickly. Now, this next example, what I want to do is say, okay, let's take a look at this. All I want to do is see there's a little bit of difference in this. I'm still doing my ladybug problem. I look for what I'm trying to maximize or minimize, and then I notice that on this one, what I am actually trying to minimize is the amount of fencing. So that's a little bit different. So when I go to my setup, I'm not doing area anymore, I'm trying to minimize fencing. So maybe I'll call this F. Now, again, same problem, except I'm going to do this, put my fencing in, and let's remember, what is the amount of fencing that I need? If you kind of look at your constraint from the last problem, your constraint is actually becoming your primary in this one because it's the fencing that I'm trying to minimize. So I'm going to do my 2W plus L right here. That's my primary equation. And I am trying not to maximize, I am trying to minimize in this case. Then we go to our constraint. Now our constraint has to do with the area. So we want to have the area to be exactly 10,000 square inches. So what we want for our constraint is the area equal to 10,000. And how does that relate to my variables? Area is length times width. Now I can solve this for either one. I'm going to solve for L because I think that's easier, doesn't have a coefficient. So I'm just going to go L is 10,000 divided by W. We substitute it in. So your fencing formula becomes your 2W plus 10,000 over W. Now at this point I realize I don't have F defined anywhere here, so I'm going to come up here and go F is the amount of fencing, just so that I get my credit for they know what the heck I'm talking about. Alright, so now we're ready to do our calculus. So I find my relevant domain. And again, we're talking about the width. So now this one's a little bit more interesting because I don't really have any kind of values to put in that. I know that my width has to be positive, but I don't have anything kind of restricting it. And this is kind of the weird thing about this one. When I go, what's my upper bound for this? You technically actually don't have an upper bound because when you are multiplying this, you're like, I just need to have a little bit of length. But if the L is fractional, then the W can be as large as it wants to be in order to make it happen. I mean, because if this is a half, this could be 20,000 and we would still get our 10,000 there. And so the idea is you actually don't even really have an upper bound. I mean, there's realistically, you can't make L so small that you can't actually physically build it, but right now we pretty much have a relevant domain of 0 to infinity. Our derivative, a little bit more complicated than the previous ones, but not much. We would have 2 plus our negative 10,000 W to the negative 2. I'm going to go ahead and rewrite it into a fraction form, getting ready to solve, find my critical values. For this problem, I'm probably going to go ahead and go with the first derivative test, modified first derivative test, as opposed to the second, but we'll see what happens here. Our critical values, when f prime is equal to 0, would end up being when 10,000 over w squared equals 2, or 10,000 equals 2w squared divided by 2, 5,000. Gotta do a little bit more work for this one. Don't worry about the negative, because remember we're restricted to positive, so w would be your square root of 5,000. You don't have to simplify, but it might be a little bit in our best interest to go ahead and pull out our 2,500, so that would end up being 50 square roots of 2, just so I have an idea of what I'm looking at there. Now, on this problem, we can go ahead and this is always positive. I'm going to do my sign chart here just to see what we have going on. I only have to worry about 0. We're going to infinity. I have this 50 square root of 2. What happens if I pick a number down here, like even just 1? Clearly this is going to be a negative number, so I would be negative here. There's 0 there. What happens over on this side? Whatever this is, it's 50 square root of 2. When you square it, you get 5,000. 2 minus 2, that's why we're getting the 0, but so it should be positive. Actually, let me take that back. That would be negative. No, it actually would be positive because I am going to end up being subtracting a smaller number than 2 once this gets large enough, so that would be positive. And so we do have this idea we can use the modified first derivative because on the relevant domain, it's always decreasing, always increasing. You know, I'm saying it, but I'm saying the f prime and then f is decreasing and increasing. So we do have enough to use the modified first derivative. So w equal to 50 square root of 2, and our units are inches, minimizes the amount of fencing because your derivative f prime of w is less than 0 for all w in the interval from 0 to 50 square root of 2, and f prime of w is greater than 0 for all w from 50 square root of 2 to infinity. And then we just want to make sure that we answer the question. Answering the question, we have, what did they ask us? They want to know the least amount of fencing. Now, this is where you kind of get hung up. They didn't ask for the dimensions. Okay, the dimensions are going to be 50 square root of 2 times whatever your L is, using your formula up here. So we know that W equals 50 square root of 2. Your L equals your 10,000 divided by 50 square root of 2, but that's not what they ask you to actually answer. They want the minimum amount of fencing, so you have to actually go back in and plug it in. So the minimum amount of fencing would be, and then we have our formula. This is where you don't have to simplify, it really works out. We have 2W plus L, F equal to 2 times 50 square root of 2 plus 10,000 over 50 square root of 2, and then just walk away. You can simplify if you want, but you don't have to. But you want to make sure you answer the question that was asked.